So now we are going to do a different kind of experiment, now a little bit in a higher frequency range. We are going to do optical devices experiment. So the kind of work what we are going to do in this particular lab tour is modeling the behavior and the aspects of physical parameters of an optical fiber. So when I say optical fiber, what I have in my hand is two different types of fiber. The one which is in yellow color, what you see here, is a single mode fiber, and the one which is in white color is a multi-mode fiber, and they have been designed for 1300 to 1500 nanometers. This is the range in which they are being used. So the single mode fiber is mainly used for the long range communication, and the multi-mode fiber is used for the short range communication. As I said, it's in the range of 1300 to 1500 nanometers. And what you see in this very thin little thing is there are three things involved. One is there is a core, and then there is a cladding, and then there is also a protective jacket on each of these in order to protect it from some damages. And these are very fine devices, and for modeling these devices we have to use either analytical method, or you can also use finite element method. So in this lab tour we are going to look at this two different types of material. One is the single mode and then the multi-mode fiber, and we are going to model it for their behaviors and characteristics and see it too using two methods. So the first method what we will be doing is a kind of an analytical method which will explain us the characteristics, the modes what we are going to compute for this particular fibers using some of the analytical techniques. And then we will compare the analytical result with finite element method, and we will compare how good the finite element method is compared to the analytical method itself. So there are going to be two students who is going to work on this particular project. So the first part I will going to look into is the analytical method. So let's go and have a discussion with my student. So Thomas is a student of mine who was in the computational electromagnetics course, and he's going to show us what he has done using analytical method for this particular problem. So I asked him to show some of the methods that he has used to analytically compute the modes for these two types of fibers. One is the single mode and then the multi-mode fiber. So let's discuss with him and see what he is doing.
This is mainly we are doing problem is modeling the modes in optical fiber using finite element method.
Okay.
Actually, we are comparing the finite element results with the analytical results, because analytical results are very common, and we know the exact solutions of this fiber. So we are comparing the finite element results what we are getting with the analytical results.
So how are you showing how the analytical method itself is placed? That's something we would like to know.
Okay. So problem statement is find out the possible modes in an optical fiber using analytical method and using FEM method also.
Okay.
So optical fibers can be divided into different ways. One is based on the number of modes propagating through the fiber, and based on number of modes propagating through the fiber, fibers can be divided into two: single mode fiber and multi-mode fiber.
So in this case, this yellow one
is the single mode fiber.
Okay.
In single mode fiber, only one mode is propagating.
Okay.
And in multi-mode fiber, many number of modes are propagating.
Okay.
And it depends on the core diameter of the of the fiber.
So what is the core diameter of this particular?
In single mode fiber, it is less than 10 micrometer.
Okay.
Typically around 8 micrometer.
Okay.
The core diameter.
Okay.
And for multi-mode fiber, there are two standards are there. Old standard is 62.5 micrometer, and new standard is 50 micrometer.
Okay.
These are mainly communication gate fibers.
Okay. Okay. So these are, and as we said before, they are designed for certain frequencies.
Yeah, they are mainly designed for 1300 nanometer operating.
So it can go up to 1500.
Mainly there are three operating optical windows are there. One is 850 nanometer window, another one is 1300 nanometer window, and the third one is 1550 nanometer. With 1300 nanometer, where the dispersion is very less, but attenuation is very less in 1550 nanometer.
Okay.
So we are mainly using this for long distance communication. We are using 10 nanometer or any window can be used.
So basically, when you talk about dispersion, what we are talking about the group velocity versus the phase velocity. So the dispersion error will be low in the 1300 aspect, whereas the wave decay itself
attenuation will be lower in the 1550 nanometer. Okay. So let's look at the basic.
Okay. One more classification in fiber is present based on the profile of refractive index profile.
Okay.
There are two profiles: step index fiber and grade index fiber.
Okay.
In step index fiber, the core refractive index is uniform.
Okay.
And in grade index, refractive index is gradually changing.
Okay.
Like parabolic changing.
Okay.
Okay.
So we can have basically different profiles.
Profiles are
but typically you are using parabolic.
No, typically you are using parabolic. Because that parabolic profile reduces the dispersion.
So when we say profile, we are talking about the refractive index profile.
So refractive index profile.
Okay.
But for simplicity, we are using step index fiber for our simulation purpose.
Okay. So
this is the refractive index profile of the fiber we are discussing. At the core is N1. And at the flat, this is the refractive index.
So A is the diameter.
A is the core.
The core.
Radius.
So radius of the core is 8. And when the radius is less than 8, you are having a refractive index of N1. And for the cladding and the protective layer, it's going to be N2.
And N1 is greater than N2 because the working principle of fiber is total internal reflection.
Okay. So whatever is propagating gets totally reflected so that it can guide it inside the core.
Okay. So N1 is greater than N2. When we are solving the Maxwell equation for this fiber, we are getting the solution of the step index fiber is like this, where is the amplitude. There are two solutions are there: force dependent solution and sign dependent solution. And inside the core, the solution can be expressed in terms of Bessel function of first order.
Okay.
First kind. And outside the plane, the solutions are expressed in terms of modified Bessel function of second kind.
Okay.
Because this Bessel function of first kind they are sinusoidal in nature.
Okay.
And this is exponentially decaying.
Okay.
Since the power is propagating through the core, that power should be in sinusoidal form.
Okay.
Outside the core, that in the cladding, there is no power. So even some power is leaking into that part, it will exponentially decay.
Okay.
So that solutions are coming.
Okay. So show us the analytical result itself.
Before that, I will explain how it is solved.
Okay.
Right? This is the solution. When we are applying the boundary conditions, we will get the mode solution.
Okay.
Okay.
So how you will go ahead with that?
At the core cladding boundary, we are assuming the condition it is these fields are continuous.
Okay.
So when we are taking the derivative, cross side by.
So you can use the pointer to mouse to show it.
At the core cladding interface, we are finding the solutions are continuous. So we are taking the derivative, and this is the boundary condition.
Exactly.
When we are solving the boundary conditions, we will get different values of different mode solutions, and these solutions are the eigenvalue solutions.
Okay.
And each solution corresponds to each mode.
So Thomas, could you please explain us the analytical procedure for deriving the solution?
Previously, I saw the analytical solution and solving using MATLAB.
Okay.
Here the refractive index at the core is taken as this value.
So core value is 1.44.
Some value. And N2 is this value. So in practical fibers, the refractive index difference between the core and cladding is very small.
Okay.
So we can use LC approximation. LC approximation means linearly polarized mode approximation. Linearly polarized mode approximation, what we are doing is using that approximation, the in a fiber only one transverse mode is dominating, like EX or EY.
So in this case, anyone will report refractive index which is 1.44, and then you have the
N2.
N2 is 1.43. So it's 0.01 difference.
Very small. Less than 1%.
Okay.
So the wavelength we are considering is 1300 nanometer, 1.3 micrometer.
Okay.
Then the remaining parameters, K0 is free space propagation constant.
Okay.
Then that is 2 pi by lambda. Then V number is that is normalized frequency parameter.
Okay.
V number, that is one of the important parameters in fiber. That is given by 2 pi by lambda into numerical aperture. The numerical aperture is root of n1 square into minus n2 square.
Okay.
Then we are creating a mesh.
Okay.
That will include the total core area.
Okay.
For each of the modes, we are finding the solution.
Basically, you are using the integral solution Bessel functions.
Bessel functions are we are solving the Bessel function.
Okay.
And we are finding the propagation constant of each of the modes.
Okay.
That is the eigenmode.
Okay. So Thomas, could you please go to the analytical code and then explain us the initial assumptions what you're making in analytical.
Usually the refractivity for the core is taken as N1 is equal to 1.44.
Okay.
And N2 is 1.43. The difference between N1 and N2 is very small for practical hybrid.
Okay.
Less than 1%.
Okay. And this particular code, if you can go up, it's taking the assumption that we are interested in modeling this particular code, step index multimode fiber.
Step index multimode fiber.
Okay. And here the difference between the core refractive index and the cladding refractive index is very, very small. We're talking about 0.01 is the difference.
Yeah, 0.01%. Yeah, okay. Less than 1%.
And then the lambda you are using is
1300 nanometers.
Okay.
Then we are creating a mesh that
okay.
That will include that in the core area.
Yeah. So what I also see that is you are using directly the MATLAB functions, the Bessel function.
Yeah, that's it.
So it actually gives you the modified Bessel function also for this
modified Bessel function. Modified Bessel function is this is normal Bessel function, Bessel J. Okay. Modified Bessel function is Bessel J.
Okay.
Then we are solving these equations.
So we are solving the Jm and
Km.
So Jm and Km are the things that we are solving for, and they are basically given by the modified and the normal Bessel function. So Jm relates to the normal Bessel function, and Km defines the modified Bessel function. And these are inbuilt programs or inbuilt functions of the MATLAB. Okay.
Then while solving for different values of L value. In LP-LM mode, we have L values. We are solving for different L values. We are getting, for a single L value, we are getting different solutions.
Okay.
And each solution is known as LP-LM modes.
Okay. These are LP-L1 modes, and then L and M can change.
L and M can change.
Okay.
For a single L value, we will get the multiple M values. And which determine each of the modes.
Okay. So can we go and plot some of these modes, and then if you run the program, what you are getting is
this. We will get different modes.
Okay.
Actually, the modes which are supporting by the fiber, many number of modes. Since it is a multi-mode fiber, many number of modes it will support.
So this is a radial mode what you are plotting here.
Yeah, this is the first fundamental mode, LP01 mode.
Okay. So what you are going to plot is there are different two types of modes that you are going to plot.
Yeah, currently I will show two types of. One is radial mode, and one is LM mode. In this mode, this is the LP01 mode.
Okay.
L is 0 and M is 1.
Okay. So we can make sense of this mode by seeing it from the top view. We will see it better. So this is the LP01.
LP01.
Okay. So then
this is the LP02 mode.
Okay.
You can see in the radial direction only variation is there. In the azimuthal direction there is no variation. Okay. That is why LP0, that L is 0.
Okay.
And there are two variations, so there are two modes.
Okay.
So LP02. LP02 mode.
Okay.
Then
so the third one, this has the three variations.
This one is LP03.
Okay. Because there are three variations.
Three variations in the radial direction and no variation in the azimuthal direction.
Okay.
Then I will show some other higher order modes.
Okay.
This one is LP11.
Yeah.
Here we are considering the cost dependence.
Okay.
So in the cost direction, in the zero direction, where initially in this direction maximum is coming, and in the y direction zero is coming.
Okay.
This is cost dependent solution.
Okay.
This is the LP11 mode.
Okay.
In the radial direction, only one variation, and the azimuthal direction, two variations are there, but we are taking the half is the y.
Okay.
So there are two variations, 1 and 2. Okay. So L value is L by 2.
Okay. So can you also show one more of this higher order mode?
This is LP22 mode.
Okay.
In this is LP21 mode.
Okay. Repeat. So this is
LP21 mode.
Okay.
in the radial direction only one variation, and in the azimuthal direction 4 variations are there. So L value is that 4 by 3. That is L value.
Okay, these are analytical solutions, and when you zoom in, you see that the results are as good as the grid what you are using itself. Okay, so and the computation is not that heavy for this kind of problem because you directly have an analytical solution, and you are not taking any time to compute it. So it's directly
solving. That computation time is 1 or 2 minutes.
Okay. So let's look at this same problem from a finite element point of view. So let's ask Bharat to come and discuss this. So Bharat has been working on this particular problem, and he's also going to show us the finite element implementation for this particular problem. So explain us how this code is being built, and then take us step by step from the physical problem to the virtual problem that you're trying to solve.
So basically we are going to solve this problem by using finite element method in a circular symmetric geometry, that is for the fiber.
So basically what you're doing is you're taking one of the slice of the fiber and
cross section of this fiber, and then we are going to show that according to the geometry of the fiber, how many modes are possible.
Okay.
Which is basically the direct function of the V number.
Okay.
So the V number of the particular problem that we have taken is 4, 4.1.
Yeah.
So for 4.1 V number, only 4 modes are possible that we have calculated in analytical solution also from that formula. So here we have taken the core refractive index as 1.452 and cladding refractive index as 1.4505, and you see that the difference between the two is very small.
Okay.
So which is called basically the weakly guiding approximation.
Okay.
Which basically limits the number of modes possible in the fiber.
Okay.
It is a widely used approximation.
Okay.
The radius that we have taken is 10 micron.
Okay.
And the wavelength that we are going to model is 1 micron.
Okay.
Okay. So accordingly, the V number is given by this formula.
Okay.
And this basically decides how many modes are possible.
This is the normalized frequency.
This is also called the normalized frequency.
Okay.
And so the second part basically where we are going to mesh the cross section of the fiber is this. And here we are going to use one inbuilt tool of the MATLAB, which is called PD toolbox.
Yeah.
And it is a versatile toolbox where we have seen the elliptic, hyperbolic and parabolic equations. So any kind of equations can be solved, and also we can solve the equations for eigenvalue.
So it shows now the PD toolbox and how you are meshing and how you are creating the basic matrix.
Yeah. So this is our problem. So if you run this problem, it just goes to the window of PD toolbox, where we see, and gives us the meshing that is. So this meshing basically we have got with using the triangular box. So in the PD toolbox, we just use the triangular meshing.
Okay.
And we can also use this meshing in a panel.
So what you see here is this is the core area.
Yeah, this is the core.
This
is the core area.
This is the core area. This is the cladding.
This is the cladding area.
So here you have used 1.452, and here you have used 1.45 as the refractive
index.
Okay. So
here we see that the mode which is possible in the fiber is a continuous function.
Okay.
So we are using the Neumann boundary condition here. If we just double right click here.
So show us the boundary elements what you have on the edges, and then how you are defining the boundary conditions.
Yeah. So basically we have here two interfaces. One is core and cladding interface. Another one is cladding and air interface. So at the core and cladding interface, we are using Neumann boundary condition, and at the cladding and air interface, we are using Dirichlet boundary condition.
So what you are essentially doing is, in the first interface, what we are talking about here, you are forcing the normal conditions to act in a certain way.
Yeah. So basically, here the normal component of the field is continuous.
Yeah. And the other one is on the directly you are forcing the value for the field to operate in certain way.
Yeah. Here it is 0.
Here it is 0. So you are forcing the field to go to 0.
Yeah.
Okay.
So this is our force meshing. If we go with it, so we have to export the parameters of a triangular element.
You double click and show the initial mesh so that we can see that this is the force field.
This is the force field.
Okay.
So if we take the elements, if we can go to the mesh window and we can take the export mesh.
So you can export it and you get the PET.
PET values.
Yeah.
and then it will be directly taken to our main code.
Okay. So it exports the value and gives you certain parameters, and you have used the capital P, capital E, and capital T for those parameters, and you are reading those parameters in your main. So show us how the main code is operating.
So this is our main code.
So this code is to demonstrate the finite element procedure to solve for modes in the step index driver.
Yes.
And you are basically taking the value. If you can highlight this one.
Yes.
So you are taking the value of the PET from the PDE toolbox, and then you have assigned the value for N1 and N2, and you are taking the value of lambda to be 1, and this is 1 micron is your lambda, and then initializing the normalized frequency, and now you are going into the loop to calculate the various aspects. So explain us what is happening in this code.
Yeah. So this is the normalized x coordinate of all nodes that we have exported from our PDE toolbox, and here we are taking the y coordinates of those nodes. So here we have two matrices. We have initialized two matrices for all n values, where capital N is the number of nodes.
Okay.
Then here we are taking the area. The sigma is the area of each element, which is triangular. So once we calculate this, we use this particular area and we calculate the weighting function for the triangular element.
Okay.
So here the normalized beta we have calculated, which is the normalized the age vector in the fiber.
So this B is the normalized
normalized age vector.
Okay.
So while forming the coefficient matrix, we calculate the C matrix, which is our coefficient matrix, and we use the sigma, which was to normalize each weight function, and we are using the quadratic weight function, which is the eta, which are the y value of each node, and we are taking the difference between two and taking its square. So our weight function here is basically quadratic. Then similarly for this loop, we are calculating this value for all the nodes. So like here we have 3, 2, 3, 1, 1, 3, and all the nodes. Similarly, we AND it, and then on the other side of the right hand side of the equation, we are calculating the D matrix. Then if you go down, and we have these equations where dA equal to C, taking the inverse of the matrix, and we are calculating the particular field value.
So you are using the inbuilt MATLAB function for inverse.
Yeah, we are using the inbuilt MATLAB function, and this value is used to calculate the eigenvalue. We are plotting the values that we have gotten, that you can see by the surface plot.
So what is this V value here? You are additionally V is the vector.
V is the vector value that we will plot for different nodes.
So run this code.
So if you run the code, so all the nodes are generated. So let us see one by one all the nodes. So this is our first node.
So 1 second. So what we see here is the first node, and we can compare it with the analytical solution what we have. So this is the analytical solution which we saw before. Actual result what we are getting from the finite element method. So we have to also show so you can see that the analytical method is having fine resolution to get the result in a nice manner, especially at the tip. And here you see that your grid is showing. You see a very sharp triangle.
This sharp edge that we are seeing, we are not seeing smooth surface. So that is because we have taken the coarse grade.
But we have now run the code, and we are able to see some results. So for example, in this case, what you are seeing is one of the modes, the radial thing. What you are plotting here is the amplitude, and we are able to see the same result in the analytical code, and we are able to see that it's much more finer compared to what you are having here. So could you please explain us how you understand or why you see this discrepancy?
Here the meshing that we have taken is coarse. So due to that, we are not seeing the complete smoothness in the tip, but maybe we can find it if we use a finer mesh. We will show that later.
So let's see also for higher modes. For example, in this case. So this is the analytical solution what we got. So can you show us the comparable finite element solution?
So here this solution is comparable to the analytical one. So there we also see the 4 loops that we
Okay,
can show.
so maybe you can show it in the right way so that it's easy for us to compare. So this one is, so we are seeing the XY plane. So here we'll also do the same thing. We'll see XY plane. So on the, so this is the two results of the same modes. One is what you're seeing here on the left hand side is the analytical result, and then you're seeing the finite element result. What we see is there is a slight shift in the mode itself. Let's say around the 45-degree shift. So could you please explain why is this?
The modes that we get are cost dependent and sign dependent. There are two functions to the boundary value problem. So here, when we superimpose them, we get a shift in the pattern.
Okay.
So that shift we are noticing here. And also we notice that on the edges, the mode value is not very smooth.
Okay.
That is also due to the post mesh.
So, for example, what you're saying is if you zoom in, you see the triangles.
Yeah.
So this one you can see that it's one of the triangles here, sitting here. Whereas in this case, it's a bit more smoother. So what we can do is we can refine the grid. So initially you had a grid which is given by certain discretization. Refine the grid and then run the same code and then see the results.
So for that we have to run the code again. So this is our original code. So let us run it again. We get again to the PD toolbox where we get the original code state. We can refine it by this refine mesh tab. So we can refine it. We have defined it sufficiently. So let us export the PET parameters again. So we export the PET parameters. So let us run our main program. We'll store with these defined parameters.
Obviously, it's going to take a little longer because you have more number of elements.
So the computation time has been increased.
Okay. Now we can see again the results. We have got all the different modes. So let's go to the first fundamental modes and see where the differences are. So we have the analytical solution again. Let's see the result in. So this is the fundamental mode, and then shows the comparable result for the finite element. You can just go here. So you are able to see that the mesh has become finer now, and also now in the initial case what we saw is a very sharp angle on the tip, but it's become more smoother. Obviously, it still has certain small triangle. But this is something that is much finer than what we had before. So what we see here is much smoother. And in the same case, we can also do the same thing for the analytical solution. And can you also show us also the higher order modes what we have?
That we have got. And here again the meshing has improved the angular part, because we have gone into the final one. So if you see, then
so maybe you can see also in the XY plane.
So again, if you see the XY plane, so this triangular portion that we were noticing before has been improved, and we get a kind of smoothness in the surface.
Okay.
So this is the direct result of the finer meshing.
Okay. So the error is converged.
If we go further finer, then this will be further improved. But again, our computation cost will be quite large. This is not desirable.
So thanks a lot for showing both the analytical method and also the numerical method. One last question is, have you also tried doing some experiments to compare the numerical results with experimental results?
So we have done experiments with these fibers in our fiber optic lab, where we have launched a Gaussian profile from a laser, and we have used a detector to see the intensity patterns of these fields. And we have found that indeed we get these LP modes, which are linearly polarized modes, and the results are basically confirming what we have simulated with finite element method as well as the analytical method. So basically, there is no discrepancy between the results.
So it's good that you are able to also see similar patterns in terms of experiments. And obviously, in analytical method, you are able to have more accuracy than the finite element method. And it's good to see some of these results and see how we can manipulate the PD toolbox to get much finer results as much as we want. So I thank both of you for taking part in this lab tour, And thank you for showing us also both the analytical method and also final element method implementation of this problem. Thanks.